So children, we are into the discussion of modern periodic table. So far we have made the periodic table, we have discussed the groups, we have discussed the periods. Now what we will do is we will talk about the lanthanides and actinides. Now before that, I would like to tell you why hydrogen is not anywhere over here. Actually speaking, hydrogen, if you think of it, its atomic number is 1. So its configuration is 1s1. So on the basis of that, it should be there in the group 1, and earlier it was placed in the group 1. But then the argument was that lithium, sodium, potassium, rubidium, cesium, francium, they all are metals, but hydrogen is not a metal. And since hydrogen is not a metal, therefore it could not be placed along with the other metals. Correct? At the same time, hydrogen gains one electron sometimes, like fluorine, chlorine, bromine, iodine, but it doesn't behave, its other behavior are not like all those halogens. So hydrogen ना तो metal है, ना तो typical non-metal like fluorine, chlorine, bromine, iodine है. So then what to do? So then it was decided that hydrogen will be placed separately in the periodic table, and that is why in your textbook it is not given, I think, but in some of the good periodic table you will find they have placed hydrogen like this on the top, and they said this atomic number 1, this hydrogen, and configuration is 1s1. So it doesn't belong to any of the groups. That is what is the explanation about hydrogen. Is it okay? Now I am coming to the remaining part, that is lanthanides and actinides. Now how these are all called as series. So I have already told you these are called as periods of series. Now this series is called as lanthanide series, and because they are after lanthanum, and this is called as actinide series because this is after actinum. And how this series are made, so that for that I have to understand the electronic configuration. So I'll rub off here so that I can manage little space and write the electronic configuration, and let me see how I can go about it. Now if you ask me the configuration of barium, so barium atomic number is 56. If you remember the above principle, so electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, then 4p6, then 5s2, if you count it will be up to 38 electrons, then 4d10, then 48 electrons, then 5p6. So when you write 5p6, I'll write here 5p6 here, 5p6. So when you write 5p6, so 54 electrons and then 6s2. This is for barium, and outer configuration is ns2, so it is placed in group 2. Then come lanthanum. Now after 6s, the orbitals which are vacant is 4f, and then what should get filled up is 5d. So now you come to lanthanum. So lanthanum atomic number 57. So this is up to electron number 56. So logically speaking, the electron number 57 should go to 4f, but somehow lanthanum breaks that rule and he fills the electron not in 4f but in 5d. So here is the electron number 57. Is that okay? And then lanthanum ends up with electronic configuration of outermost configuration of 6s2 5d1, and because of that the configuration it is coming to is ns2 n-1 d1, and group 3 configuration is ns2 n-1 d1, which I have already discussed, and it is on this basis lanthanum is placed in group group 3. Is that okay with you? Okay, lanthanum has broken the rule and got itself placed in group 3, but after that the next element, atomic number 58, cerium 58, it says no, I will not fill the electron in 5d, I will fill the electron in 4f. This happens because of because of the energy factor. All these explanations are given on the basis of energy factor or stability factor. So the electron number 58 comes here at 4f, and it becomes 58 electron comes to 4f1, and therefore its configuration becomes 6s2 5d1 4f1. Now if you ask me, its behavior will mainly depend upon outer configuration. This 6s2 5d 4f both under hai, and therefore it will not play a very vital role. It will play a role, but not a very vital role in its apparent chemical and physical properties. And that is why this element was not discovered for a long time. For a long time it was thought to be actually lanthanum. Then comes plasmodium, that is atomic number 59. Now atomic number 59, it fills up the electron here to make 4f2. Then 4f3, 4f4, 4f5, 4f6, 4f7, 4f8, 4f9, 4f10, 4f11, 12, 13, 14. And that means they all end up with configuration of 6s2, 5d1, 4f, 1 to 14. So here the electron is, last electron has entered the 4f, and that is why when I write the outermost electronic configuration, I have to write 6s2 because it is the outermost shell, 5d because it has remained incomplete, and 4f because last electrons are going to the 4f. That's why entire thing I have to write in the outermost electronic configuration. But if you ask me, the behavior will depend upon more on 6s2 5d1, that is ns2 n-1 d1, and that is why they all are considered to be additional members of group 3. I hope you understood about this. And since these elements have followed lanthanum, that is why this series which we put separately is called as lanthanide series, because after making the periodic table there was no way the periodic table could be disturbed. So it was said, let us put it separately and put an arrow saying that it is the legacy of lanthanum. Now you will ask me, what about actinide series? So for that, let me write the electronic configuration of actinum, atomic number 89. So when you come to 4f14, so 4f14 is 71, then 72 becomes 5d2, then once again 5d gets filled up, so this becomes 72, and then its configuration becomes 6s2 5d2, ns2 n-1 d2, and that is why hafnium is placed in group 4. Is it okay, children? Then then this goes on, then up, then 5d10. When it becomes 5d10, so this will become 72, 73, 74, 75, 76, 77, 78, 79, 80. That is mercury, 80. Then after that 5d2, after 5d2, the next orbital which is supposed to get filled up is 6p. So then 6p, this is 80, 6p 6, that is 86. This is what ns2 np6, and that is what happens for radon. Then after that 7s1, 7s2, that is 88. 88 is the configuration of which one? It is for radium. And then actinum 89. After 7s, the orbital to be filled up is 5f, and after that 5f, and after that 6d. Somehow actinum also does the same mischief like lanthanum. He says, I will not fill the electron in 5f, but I will fill the electron in 6d. So it becomes 6d1, and its atomic number 89. So actinum ends up with electronic configuration of 7s2 6d1, that is ns2 n-1 d1. So actinum is placed in group 3. I hope you're clear about it. Now comes thorium to lawrencium. I hope you understand. Thorium says, no, I will fill the electron in 5f. So it becomes 5f1 and that becomes 90. Then next one, 91, it becomes 5f2, 5f3, 5f4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And then they all fill up from 1 to 14. And therefore, for thorium to lawrencium, the configuration becomes 7s2, 6d1 and 5f, 1 to 14. This is why their behavior also will depend upon 7s2, 6d1. That is, main behavior will depend upon ns2, n minus d1. So they are considered to be an additional member of group 3. But they again, placing them become difficult. So they are placed separately down here. And this series is following actinum, and that is why this is called as actinide series, or they are called as actinides. And if you ask me what is their configuration, 7s2, 6d1, 5f, 1 to 14. And that means common outermost electronic configuration for these elements is ns2, n minus 1 d1, n minus 2 f, 1 to 14. F orbital, when it gets filled up, it is n minus 2. I hope you get my point. And that is how here S1, S2, P1 to P6, D1 to D10, and here F1 to F14, F1 to F14. And I must tell you one more thing. These are called as absolute metals. Here they are becoming more and more non-metallic. It is through this series of group 3 to group 12, the property changes from metallic to non-metallic property. Change is called as transition, and that is why these are called as transition elements. And each series is called as transition series. This is the first transition series, beginning with scandium, beginning with yttrium, second transition series, beginning with lanthanum, third transition series, beginning with actinium, fourth transition series. And these two series have come within the transition series. Therefore, they are called as inner transition series. Is it okay, clear, children? So now, if you ask me the electronic configuration, NS1, NS2, NS2, NP1, NS2, NP2, NS2, NP3, NS2, NP4, NS2, NP5, NS2, NP6, except helium. This is NS2, N-1, D1, NS2, N-1, D2, D3, D4, it can become NS1, N-1, D5. Then NS2, N-1, D5, NS2, N-1, D6, NS2, N-1, D7, NS2, N-1, D8, NS2, N-1, D9, NS2, N-1, D10. And here the configuration is NS2, N-1, D1 constant, and then N-2F, 1 to 14. That is why when you do the blockwise classification, the last electrons over here have gone to S subshell. So this is S block. The last electrons have gone to P subshell. So this is P block. Last electrons have gone to D subshell. So it is D block. And here the last electrons have gone to F subshell. So this is F block. That is how the periodic table is classified blockwise: S block, P block, D block, and F block. Is that okay, children? So that is all about the periodic table. In my next video, I will be once again revising the electronic configuration on the basis of the group, and then we'll talk about the salient features of the periodic table. Is it okay? Thank you. Thanks a lot. God bless you.